Hello everyone, I want to tell you about our paper on directed flow augmentation with Jung, Stefan, Kratsch and Magnus Wahlström. So our favorite problem today during the talk will be a variant of the minimum ST cut problem. So I'm going to cut edges during the talk only, so all edge cuts are edge cuts. If you want to cut S from T, cut all S to T paths with minimum number of edges, this is a known polynomial time solvable problem. For example, on this picture, you need for example, cut these two red edges in the middle, and that would cut all the paths from S to T. Polynomial time solvability survives if you add capacities on or weights on edges. If you want to cut edges of minimum total capacity or minimum total weight, then the problem is still polynomial time solvable. But on this picture, the optimum solution changes to, for example, these four edges here. Okay. But I want to ask the question, what happens in between? What do you do if you add both the cardinality bound and the weight bound? That is, I want to find a minimum weight cut among the guys of cardinality most k, where say k is 3 on this picture. And so what happens then? This is like, you should think of it as a cardinality being some small integer. We'll shortly do FPT algorithm parameterized by the cardinality. But the weights are just big numbers, big positive integers that you can add up, and they are written in binary and they're quite strange and complicated. So in this picture with bound 3, actually you want to cut these 3 edges, for example, that gives you a cut of weight at most 8, and I think that's minimum. But this problem becomes a bit hard if you do both constraints. And what, so this problem, let me phrase it formally. You have got S and T, you have got weights on edges, and you have got the cardinality bound and weight bound, and you are looking for a cut satisfying it. But the good way of thinking is that the cardinality bound is something fixed, like you want to cut the most k edges and you want to minimize the total weight because the weights are strange numbers here. Okay. On this picture, we have got the example that this edges got weight 8. Okay. As I told you, it's NP hard, and the reason why it's NP hard is because bipartite vertex cover with separate badges on the sides is NP hard. I mean, if you know bipartite vertex cover is NP hard, it's a polynomial time solvable, but if you separate the badges for the left side and the right side in bipartite graph, then it becomes NP hard then, and this is the same problem, essentially not the same problem, but this is a generalization of this problem. Okay. If the weights are actually still small integers and you actually think of the weights as being additional parameter, then you can actually think of edges of 2 colors, and you have got separate badges for the 2 colors for the cut, and then this problem becomes polynomial time solvable because FPT, it's a bit hard, but it becomes FPT because of the generalization of importance separators. So there's the tool called importance separators parameterized algorithm, and it generalizes to like having a constant number of budgets for different colors of the edges up there. You can see solid polynomial time in FPT time. But the question here comes, what happens if only the k is the parameter? And as I told you, the weights are strange large numbers. And in undirected graphs, you can still solve it in FPT time because of some quite advanced tools that understand the structure of all minimal cuts from S to T. I mean, there's something called tree reductions, which says that all these cuts essentially live in a part of the graph that have got bounded tree width. And there's also a tool called randomized contractions, which somehow like recursively contracts parts of the graphs that can't be separated with small cuts and shrinks the graph to constant size in the end. Okay, so there are tools in other directed graphs, but they don't want directed graphs. And yeah, so the goal on this paper is sort of provide a tool that works in directed graphs. It's very different than randomized contraction tree reduction, but sort of understand the space of all ST cuts or minimal cuts of bounded size from S to T in directed graphs. So the starting observation is that this problem is polynomial time solvable in the special case when your cardinality bound is actually the minimum you can hope for. So if the minimum cardinality of an ST cut is 2, then it's actually easy to find a minimum weight solution among the guys of cardinality 2, of minimum possible cardinality. How do you do it? Well, you use the capacitated version, and you put the capacity on an edge being some huge number plus the weight. So the huge number is like all the weights in the graph plus 1 or something like that. And you put the capacity of an edge to be the huge number plus the weight. And this really corresponds to every edge having like capacity 1 dot, and after the decimal, long time after the decimal point, the weight of the edge. Okay. And now if you want to optimize the total capacity or total weight of the cut, your first optimizing the cardinality, and that goes down to k, you cannot get better, and then you optimize the weight as a second factor, as a second coordinator, and this gives you the solution here. But this works for k being like the size of the minimum, the cardinality of the minimum ST cut, but it doesn't generalize to larger k easily because it's FP hard. I mean, it doesn't generalize polynomial time. So what we would like to do here is that we would like to have an algorithm that sort of like, okay, in FPT time, turns an instance when k is some number into an instance when k is the minimum possible cardinality cut. Yeah, and that's exactly what we do. We have got a randomized polynomial time algorithm, so it's polynomial time, but the success probability is f of k, 1 over f of k, so that would be FPT algorithm event. So there's polynomial time algorithm that takes this graph, and there's some unknown solution, here the red one, but it's unknown to the algorithm, a minimal cut, an inclusion-wise minimum from S to T, and the algorithm, the only thing it knows, it has got cardinality at most k. The solution we're looking for has cardinality at most k, and it randomly adds the edges to the graph. So adding an edge can only destroy the solution. It won't create new solutions, only destroy some of the solutions. And the promise is that with good probability, 1 over f of k here, 1 over f of k here, with good probability, a solution we are looking at, we want to find, one fixed solution will become a minimum cut. So we will turn a minimal cut into minimum cut. So we will push some additional flow from S to T to saturate all the edges of our intended solution, of our solution we are looking for. So for example, on this graph, adding these 3 blue edges increases this flow from S to T to 3, but the red is still a minimum cut, so it's still an ST cut, so it becomes a minimum cut in this process. Okay. So that's what we do, and that's like the complicated theorem inside up there. But now let's look formally how it works in practice. So let's go for the problem we want to solve, this bijective ST cut. So if we have got this instance, okay, we have got this success probability of the flow augmentation. So we repeat the inverse number of times, so that there's a constant probability that one of the iterations will actually get our solution we're looking for, will turn into a minimum cut. And adding an A doesn't create unwanted solutions, it only like destroys some of the solutions. But with constant probability, in at least one iteration, a solution will actually survive in the graph, and we'll actually find it by looking at the minimum possible, cardinality solution in the graph. Okay. So we have got the bi-objective ST cut is randomized FPT parameterized by k, and the f of k function is roughly this one. Okay, so that's what we have here. A few things to be noticed. In this theorem, we can actually add arcs in both directions at the same time. We really argue that with this probability, we are connecting only the guys on the S side of the cut and the guys on the T side of the cut. So the edges can be, they're of course undeletable in the sense that, I mean, they're not part of the solutions. You really can think of them as like connecting S side or connecting T side. You can actually merge these guys to one vertex if you prefer. We didn't really optimize the exponent, but there's a potential, there's quadratic potential in the recursion that we do. So we don't think with our tools we can get better than k-squared in the exponent. So no, it's like 2 to the k or no k factorial or something like that. No, we really, if we think with the current tools, we really need k-squared in the exponent. It's randomized, but we didn't put much effort yet into making the randomized. I think there's no good obstacle to the randomization. It's just a stack of color coding trees, but they're quite delicate in a few places. So it's actually a non-trivial exercise to go with all the color coding, the randomization tools, and check that we can actually do it. We plan to do it, but we didn't do it yet. So we can't claim a deterministic variant of this algorithm. And there's a slightly more general version that actually, if this cut that we're looking for, it has got S and T, and there's a cut. This is the cut, this cut Z that we want to preserve. The cut is actually allowed also to cut away some parts of the graph that will be not reachable from S, but they're not needed to separate T. So with this we call a start ST cut. The definition is formally that every edge of the cut has got a tail reachable from S, but the head is not reachable from S, so we actually separate something from S. Okay, and we actually can guarantee that our connections, not only our added edges, not only make this part a minimum cut, but also doesn't break this additional like extra part. And this is needed for some of the applications that I don't want to speak about today. So I mean, there's some generalizations that work for some problems, in some sense making S more important than T, but I don't want to go into details now. Okay, so we have got this one. We had a previous paper on Soda doing this for undirected graphs, and undirected graphs, there are actually some problems that we don't know how to solve with the randomized construction and these type of tools, which actually also need flow augmentation. But I want just to say that with undirected graphs, the proof becomes simpler and you get like k-log index exponent success probability there. So if you want to use this for undirected graphs, you should look in the previous Soda paper and get a better success probability. Okay. So I want now to tell you why I think what does it mean that this is actually really a space of all mean cuts here, that you are actually doing a space of all mean cuts. You're understanding the space of all mean cuts. It's not really space of all mean cuts. It's like you take all the not inclusion-wise minimal cuts. So in a sense, I wanted to understand the space of all inclusion-wise minimal cuts from S to T. It's not really understanding the space of all of them. I am applying flow augmentation, and then I have got some understanding of the guys that survive flow augmentation. Flow augmentation adds some edges to the graph, so it kills some of the cuts from S to T because there are some new edges. So there are less cuts. But some of them, of size in most cases, survive and become a minimum cuts. This one for which the success from was successful, and this gives some description of the space of them. So to understand it, let's look just at the space of all minimum cuts. So I want to have S and T, and I want to understand the space of all cardinality minimum cuts from S to T. So how do I do it? Well, I compute the maximum flow, say this paths maximum flow. I can show vertices or edges joined, but let's draw them like that. And the minimum cut actually like cuts one vertex per flow path somewhere. Okay, that's something. So we can think of it like as a flow path is a slider or a variable in the CSP language where you cut it. Okay, it's a slider where you cut it, but there are some constraints. Okay, there are some constraints like if, for example, you can go from here to here in the graph without using any edge of the flow path of any flow path, then it means that the cut cannot be like on this picture, because now on this picture you could have go here, go by this path and go to T, and that would be a mean cut. Okay, so if there's such a path from this U to this V, then this constraint, this thing really says that you either cut here earlier, or you cut here later than the space. You cannot like cut the other way around as in this picture. Okay, so it really says the constraint of this form, okay? That the way where you cut the first path is earlier than you, or how you cut the second path is later than you. And you have got this type constraints, and you write these constraints for each such connection, actually really each endpoints of these connections for which there's path, you write such a constraint. And this, if you look at the path closely, this CSP, so you think of this like being lambda variable, so for every flow path there's a variable, and you think of this as like you write all these constraints, and this exactly like the space of the feasible solutions for the CSP instance is exactly the space of all estimated cuts. Okay, and the intuition that I want to convey here is that now we have the same description for the space of all inclusion-wise minimal cuts. Not all of them. I mean, in the sense that there is like this flow augmentation routine that looks at all minimal cuts, samples something so that only a few of them survive this flow augmentation, and then for the one that survive the augmentation, you have got this description because now there are minimum cuts. Okay, so there's this way of thinking it, and it actually is helpful. So let me do some applications. So sorry, let me do some applications. I mean some cut problems where now forget weights for a moment. I mean there will be weights later, but forget weight for a moment. But now I want to have cuts, but I want to count the cardinality of the cuts, but not exactly the cardinality. There's some like sales happening. Some edges are grouped into bundles, and you pay 1 to delete the entire bundle. Okay. In other words, you want to find a cut that violates as few bundles as possible. So I want to think of finding an inclusion-wise minimal cut that violates as few bundles as possible, so that you need to buy as few bundles as possible, like at most k bundles. And this problem quickly becomes NP hard, and we want to ask the question about FPT tractability parameterized by K. Okay, and well, what are the interesting cases? Well, in the bundles or singletons, there's no sales happening, and this is just a minimum cardinality cut. The point is that whenever the bundles are just arbitrary pairs of edges, so you get one by one, get another for free, then this problem is already double and hard. So if there's just arbitrary two edges happening like in a bundle, then this problem becomes double and hard. But there's an interesting case when a bundle is a path. So a bundle, I mean, there's a path. The graphs are the edges of the graph are arranged in the paths of constant length, like length 3 think of them as length 3, and you're paying 1 to like violate all the edges for the bundle just for one, and you want to violate in most cases bundles. And this actually becomes, this dominant hardness doesn't apply here, even with the paths of length like 3, 4, 5 there. And this actually was defined almost a decade ago by Hittins against Maleks in some homomorphism problems, which is quite surprising, but completely different set of problems. And the FPT status of that one was repeatedly approached since then, and we actually solved it. So we actually showed that this problem, this is like here written formally, this problem is FPT using flow augmentation. And what I want to say here is that the interesting case, without going to details, the interesting case is really 3 edges. So for one edge, for paths of length 1 and 2, the problem is easy. And the first interesting case is when the paths are length 3. So you already have got bundles looking like that, or maybe think of them as looking like that. And you really want, because really you can gain by hitting the first and then the third edge usually. And this is like the problem. Is this problem FPT? Okay, and it is FPT. So this is the formal statement of the problem. And the point is that, okay, using flow augmentation, you just apply flow augmentation, and with good probability, your cut is a min cut. Okay, so there's a min cut violating at most k bundles. Okay, that's the thing you get from flow augmentation. You've got this picture that you have got a min cut. It's also of size at most 3k because every bundle is of most size minus 3. You can argue that it's at most 2k, but it doesn't matter. You have got your flow. You have got your flow, and now on every edge, every flow path, you cut one edge. So I'm trying to use the description I showed you previously about like sliders on every flow path, that you kill one edge per flow path, but you're doing like you're kind of, but you want to violate at most k bundles. So there's somewhere bundles here, and you want to violate at most k of them. So since the number of flow paths is bounded in parameters, like at most 3k or 2k, you can actually guess how they're partitioned to bundles. So you can guess that actually it will look like that. I mean, you don't know which bundle it is, but you will know that the first path and the second flow path will be together on a bundle like that, and this third and the fourth one will be together in a bundle like that, etc. There's something like, you know, k factorial or something like that, choices for that. So, or k to the L, blah, blah, blah. So that's bounding parameter. So we can guess actually how they're partitioned to bundles. And now comes the crucial thing. I mean, so, and now we're looking for the solution that looks like exactly like that. So we're looking at the min cut, okay, that looks like that, like on this picture, so that these guys are together in a bundle like that, these guys are like that, and these are like that, and they will be together at most k bundles because you guessed it to be at most k bundles. Okay? And the crucial observation is that if you now, after this guessing, you look at the bundles that are still possibly in your solution. You're looking here and you're saying, okay, which guys can be possibly in the solution? The observation is that if you have a candidate looking like this and another candidate looking like this, then the first one, the violet one, I think, is not really a candidate, because if you cut this edge and this edge, then the gray guy actually gives you a bypass from S to T. Okay, so you can say, okay, the violet one is not really a candidate. This is not I don't want to use this bundle. This bundle becomes undetectable. I don't like it. Okay. So once you do this filtering, suddenly the bundles become ordered like that. I mean, these are the remaining candidates. I mean, they cannot cross. I mean, if they cross, one of them is no longer a candidate. So they look like that. Okay, and this happens for all the paths you guess that are together. And this really says that these paths are all together. I mean, this really says that this variable, the slider here and the slider here is the same slider. I mean, you have got like, you can merge these two sliders to one, these two variables to one, and have got a CSP instance of the same type, but now the slider is not a single path, but it's like a bunch of paths that have got consecutive guess, and you have got the same description of the space of the min cut. In particular, you can check if it's empty or not by just minimum flow, minimum cut, maximum flow algorithm after. Period. The point is that this also, okay, in the end, it's like a two-satellite problem, but also think of this as a flow problem. The point is that you can do it with weights. That's the interesting thing. You can solve the final problem. The final problem also can be reduced to like minimum capacity cut, and then you have got weights. So like you want to violate at most k bundles of minimum possible total weight. Okay, so you have got even a weighted change of being FPT here. Okay, so that would be done. And we said that we were in the weighted setting. What I want to say is that with essentially the same algorithm, we can also nail down the weighted directed feedback vertex set and the related problem of weighted skew multicut, which was another problem that was asked a few questions. So I want to delete the most k vertices of minimum total weight to get an acyclic graph. So previously we knew only one FPT algorithm for directed feedback vertex without weights. It had a greedy step that didn't work with weights, and now this is a different algorithm. We can get a different algorithm for directed feedback vertex set that now handles weights, which I found nice. And the point is that directed feedback vertex set reduces by standard tricks to skew multicut, which is some variant of the multicut problem. And the point is that the multicut problem can be embedded as a very similar thing to chain set that actually has got essentially the same properties and more or less the same algorithms for the chain set works also here. So we have got an FPT algorithm. Okay, so we have got that one. And that's it, we are prepared for this talk, but there are some subsequels in preparation where flow augmentation will be applied to another problems, not in this talk presentation, but later. So stay tuned, there will be more applications of this thing in the near future. Thank you.